last year I've been teaching to myself via Zoom for a while. So it's really a pleasure to see some faces in front of me. So this course is a course on statistical mechanics, on basic statistical mechanics, but not too basic. Okay, it's not too elementary. My name is Alessandro Silva. I'm based at CISA, but I have an email at ICTP. So if you need, if you have questions or something concerning the classes, I invite you to use the ICTP, my ICTP email. Well, if you need me, if you need to call me, I will be most of the time at CISA. So this is my phone number at CISA. Well, in the days in which we have classes, I will be sitting in ICTP, and if I remember correctly, my room at ICTP is 3 or 4, but I have to check. I don't remember the number at the moment. Okay, so this is a course on statistical mechanics. What is statistical mechanics? I expect that you already know to some extent. How many of you, I don't know if those who are connected via Zoom can answer this question, but how many of you took a course in statistical mechanics before?
Yes.
Everybody. You didn't take a course in statistical. Did you take a course? Yes, you took. Okay. What about the other guys who are connected via Zoom? Everybody took a course in statistical mechanics? You can turn on your mic and answer this question. Okay, no answer.
Yeah.
Yes, excellent. Wonderful. Okay, so therefore, well, this is good news because it means that you already know the subject and therefore we will be very advanced. Okay? No, I'm joking. All right. So what is statistical mechanics? You know, actually, statistical mechanics was invented to connect two fields in physics. One is Newtonian dynamics, because in those days they didn't have quantum mechanics. So microscopic physics, microscopic dynamics, the theory of motion of particles, and etc., Newton's laws and Newtonian dynamics, and so on and so forth. So they wanted to connect this with the laws of thermodynamics. Thermodynamics, which is a theory that was invented essentially when in the years where the Industrial Revolution was running, and when people wanted to try to understand something about how machines, how engines work, and how substances change, and what it means to deliver heat, what it means to do some work, and so on and so forth, to put all of this on solid mathematical grounds. Now, the connection between microscopic physics, Newtonian physics, and thermodynamics is called statistical mechanics, StatMech for the advanced students. StatMech was invented by a number of people. The most prominent one who actually had a fundamental role in inventing statistical mechanics was Ludwig Boltzmann, who had the idea of connecting the concepts of microscopic physics, so phase space, motion of points in phase space, Newtonian dynamics, Liouville equations, and so on and so forth, two concepts in thermodynamics through a beautiful formula, the formula for the entropy, written down by Boltzmann, that is actually so beautiful that is even engraved in his tombstone. So it's actually the defining work of this person. He did a lot of work actually, but But this formula is truly amazing. Anyway, so in order to understand all of this and to appreciate statistical mechanics, we will need a few prerequisites, right? So I'm not going to teach you Newtonian dynamics. I assume that you know what is Newtonian dynamics, what is Hamilton dynamics. All of that is familiar to you, motion of gases, blah, 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 particles, in potentials, and so on and so forth. Classical physics and quantum mechanics. I know that you're taking a course in quantum mechanics. I don't know why here is becoming everything yellow, but by the time we will reach quantum statistical mechanics, you will be more, a bit advanced in your course in quantum mechanics, so you will know what I will be talking about. Anyway, so microscopic is taken for granted, microscopic physics. Now, I will certainly give you a review rather in depth of thermodynamics. Now, I know by experience is not the first time, as you probably know or can see now that I teach this course here. And then my experience is that thermodynamics is a subject that scares students, because thermodynamics is a subject that is hard to understand. It's hard to understand what we are talking about when we talk about thermodynamics. Why? Because our brain, our way of thinking is already oriented towards statistical mechanics. The way we teach physics, we start from basic microscopic things, Newton laws, quantum mechanics, and so on and so forth. And thermodynamics is a rather abstract and obscure subject. Okay, so I will do my best to make out of this obscure subject a simple thing. Okay, so I cannot promise that you will understand the thermodynamics, 100% at the end, but I will promise that I can promise that I will do my best to make you understand all the concepts of thermodynamics. Yes.
Do you want to turn off the light?
Yeah, we can turn off the light anyway, so it's, how do we do that? Here?
Yeah.
Like this?
Yeah.
Like this?
Yeah.
Okay, good. This way you don't fall asleep. Okay, excellent. So we will do therefore a review of thermodynamics. But before reviewing thermodynamics, since the connection between microscopic physics and thermodynamics is statistical, and statistics means that we will have to use concepts from probability theory, the first thing I will do is 2 lectures in which I will essentially review some basic concepts of probability that you probably already know, but it's useful to set a notation and understand various things. And in particular, in the second lecture, I will immediately introduce the concept of entropy. Why? Because the concept of entropy actually can be introduced nowadays starting from a different point of view, which is not the one of thermodynamics, in which you never understand what we are talking about because it's obscure. It's a state function, blah, 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 that always increases in adiabatic, and it's complicated. Nowadays, it's actually much easier to understand what is entropy, introducing it in the context of information theory or probability theory. And in that case, you understand very well what is entropy, what it means, and what is its significance in connection with probability distributions. Then we will start the long journey through thermodynamics. And I will go through all possible cycles and engines, the Otto cycle, the Carnot cycle, the blah, blah, blah. I know that you're familiar with those cycles, right? So we will go through them slowly, adiabatic processes, isentropic processes, blah, 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 and do a lot of exercises, okay? Why? Because typically in the final exam there is always one exercise on thermodynamics. Okay, so you have to know thermodynamics. After we finish thermodynamics, we will go through classical StatMech. Classical statistical mechanics. So we will essentially introduce this connection based on classical dynamics, Newton dynamics. Now this is not mandatory. The newest books on the subject actually start from quantum mechanics, but pedagogically I think it's simpler to start from classical mechanics also because it will give us a chance to describe, for example, some toy models which are frequently used in statistical mechanics, such as the Ising model, the Potts model, what is mean field theory, what is the cluster expansion, what is the high temperature expansion, and so on and so forth. We will essentially do an extended broad course on classical statistical mechanics, and then towards the end I will be talking about quantum statistical mechanics. And here I will not dwell too much on the quantum subject. I will just introduce the simplest possible things, which are, indistinguishable particles, fermions and bosons, show you how the statistics changes when you have quantum mechanical particles, and what are the consequences, which are essentially Bose-Einstein condensations for bosons, so the low temperature expansion for fermions. And I think last year I've done also the theory of specific heat of solids and black body radiation. Okay, so these are simple enough effects for non-interacting quantum mechanical particles. So I will not be dealing with interacting quantum mechanical particles. The only interacting thing we will be dealing with are classical gases. Okay. And we will be introducing the real expansion and so on and so forth. All right. So now, yes.
So, are we going to study phase transition?
Yes, to some extent, not in depth. So what we will be doing for phase transitions is, so I will be discussing Ising models in quite some detail because they are useful to practice computing partition functions, etc., etc., etc. Now, as you know, the Ising model in more than 2 dimensions has a phase transition between a paramagnet and a ferromagnet. We will be doing that in mean field theory, but I will not be dealing with the theory of critical exponents, fluctuations close to phase transition. Those are advanced subjects. I gave a course here at ICTP for a number of years on this, which was called renormalization, Advanced StatMech 2, or Advanced StatMech something, I don't know, or just StatMech 2, I don't remember. And it was essentially a simplified introduction to the theory of phase transitions and the renormalization. Now, at the moment I give a course which is based on that, but a bit bigger at CISA, and so we will not be dealing with RG here. Okay, it's too advanced. I have to do all the basic stuff. All right, now, books. Where can you study statistical mechanics? Apart from the lectures that you can try to learn statistical mechanics through hypnosis. So you can take your lectures, put them on a headphone, and listen to them while you sleep. And probably the day after you will know statistical mechanics. Now with this technology we can do many things. But the best books I know on the subject actually are a series of lecture notes by Daniel Arolas. You can find them on his webpage. I'm not sure they are still there. Try to check. If they are not, I have a copy, so I can share it with you because it was public when it was up to a few months ago. I didn't check recently. So it's a lecture notes on statistical mechanics. Is a rather bulky book. It's about 300 pages, but it's really very well. I mean, it's a really beautiful book. Now, the famous book on statistical mechanics is Pearson Wang. Sorry?
Patria.
Sorry?
Patria. The book by Patria.
Batria? Show me the Batria. I don't know this book.
Oh.
Oh, that's interesting. Show me.
But,
I cannot touch it.
But I asked seniors and they recommend this.
Oh, really? I didn't know. Okay, I will check it out. Anyway, so the one that I read when I was as young as you is the one by Pearson Wang. It's nice. The only problem of this book is be careful with notations. Notations. Why? Because, you know, as you probably know, everybody calls the partition function, the canonical partition function Z. He calls it Q. I don't know why. Everybody calls the free energy, the Gibbs free energy F. He calls it A. And so there is a risk of getting a bit confused if you just look at this book or read this book without reading all the chapters, or you're just interested in one little subject, because the notation is rather different from the type of letters he's using is rather different from what everybody else is using. There is a nice book by Mera Kardar. This is a graduate text, so it's a bit advanced. There are two books, Statistical Mechanics of Particles and Statistical Mechanics of Fields. You can find them in the library. I don't know, is the library, can you go to the library? Oh,
Yes.
Excellent. So if you go to the library, you can find them in the very end of the library, where, you know, you just end at the door on the right. There is a little shelf where there are all the books of statistical mechanics. These are nice books, very nice, but they're advanced. So you have to know the subject in order to appreciate them. But, you know, towards the end of this course, you will certainly be able to read this. Then there is the famous book by Fermi on thermodynamics. You know, for the brave of you who want to read antiquary books, well, you're welcome. And also for the bravest, Landau-Lifshitz. Now this is a great book. I love the Landau-Lifshitz books, but they are a bit outdated, right? I mean, they are very old. They are very deep, very synthetic. A lot of wonderful exercises, but you know, we are used to a different language nowadays. Anyway, it's certainly one of the best books on statistical mechanics still available. But you know, if you prefer Arovas or Wang, I understand it. Okay, excellent. So now, after this half an hour of nothingness, we can start with something. And we start with the first lecture on probability. So probability. Probability 1. Well, you know what is, okay, I'm not going to dwell too much into the frequency, blah, 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 all various interpretations of probabilities. Let me just state mathematically what is probability. If you take a certain set, which is a discrete number of, you know, a certain number, finite number of events, so let's call the set of events C, The probability distribution P of n is a positively defined function defined on this set, which is normalized to 1, and all the Pn's are positive, right? So sum over n, Pn is equal to 1. And we call Pn the probability of the event n to occur. What does it mean? Well, my favorite interpretation is, without becoming too philosophical, is you repeat this event many times, and you check the total number in which you got n as compared to the number in which you got n as compared to the ratio to the total number of events of repetitions, and then of course the ratio of the two will define the probability. Okay, so that's the simplest way. If you were an experimentalist, you would measure probability this way. For example, so if you throw a coin, you know that the probability, unless you're cheating, the probability of having head or tails is equal to 1/2. Why? Because head and tails are equally probable, and various repetitions of the event of throwing a coin are uncorrelated, right? So if you repeat the experiment many times, there is no correlation between what happened previously and what is going to happen in this repetition now. If instead you have a dice instead of having a coin, so a dice, unless you have those fancy dices that my kids have to play, I don't know, Dungeons and Dragons, and that have dodecahedra and various complicated, standard dice has 6 faces, right? And again, if you're not cheating, so if you don't, you know what I'm talking about. So the probability to obtain 1 or 6 is identical, and it's always equal to 1/6, 1 over the total number of possible outcomes. So this is equal to pi for all I between 1 and 6. All right, so given a probability distribution, let's see now if you remember the rules in which for composite events. So what is the probability, for example, if I throw dice twice, what is the probability of obtaining 1 or 3? 1/3, because it's the sum of the probabilities of the two events, right? So it's 1/3. And now, what is the probability of having 1 and 3?
1/36.
1/36, because it's 1/6 times 1/6, right? Because you have to have both of them. So you have essentially to divide, to take 1 over the total number of events for a pair. Okay. So I see that you remember everything pretty well. So now let me remind you, once you have a probability distribution P of n, and you have a function defined on this probability, on the mathematical function defined on real numbers, defined on the set of possible events, so let's call this function A of n, then you can define the moments of this, so moments. And the moments are defined as the average of A to the power n, so this is the nth moment of the distribution. So in practice, the way this average is defined is sum over n belonging to C, A of n to the power n is an integer, okay, I didn't say it, but it's obvious, P of n.
What's C?
C is, I define it as the set of all, you see it here, is the set of the events. right? So for the dice is 1, 2, 3, 4, 5, 6. For the coin is 1 and 2, etc., etc. Right?
AN is the function of the set of events.
Yeah, A is a function. Is a mathematical function for this set of events. I mean, I'm defining things in general. So I will show you some examples in a second. So in particular, so the first moment when n equal 1.
Is a to the power of n?
Yes, a to the power of n. Can you see it? Yes. So n equal 1 is defined as is average. A is, of course, defined as the average. Then, then you have the second moment, n equal 2, which is the average of a squared. But the average of a squared doesn't really characterize how big are the fluctuations in your system, right? Because in order to characterize how big are the fluctuations, you should compare or actually subtract from the average of a squared the square of the average, right?
Yes.
So go from what is called a moment to what is known as a cumulant, this object here. Okay, so this is the standard deviation, right?
Yeah.
Is telling you how big are the deviations from the average. How broad is your probability distribution, in a sense. So, for example, for n equal 3, you can of course define the third moment, a cube. But a cube again is not telling you how asymmetric is your probability distribution. To tell properly how asymmetric your probability distribution is, because if it's perfectly symmetric, then the third cumulant. So what you should do is compute the associated cumulant, which, if I remember correctly, is called kurtosis in statistics. So it's 3a squared a plus 2a squared. Okay? And so on and so far. So you see, you always have moments which are just averages of powers of your function. And then, but if you want to extract information about the properties of your probability distribution, what you should do is subtract from these moments some appropriate combination of lower moments, right? For example, for the second moment, just the average of the square of the average, and you get the associated cumulant of the probability distribution. All right, so let's see now.
Sorry, so for
Yes.
a cube, what's the meaning? I mean, for a square, you can get the standard deviation.
Yes.
What's the case for a?
Well, it tells you how, well, we will see it later on in more detail, but essentially, the third cumulant, for example, tells you how asymmetric the distribution is, and in particular, higher cumulants give you an information of how non-Gaussian your probability distribution looks like. Because the Gaussian distribution, which we will introduce in a second, is the super special distribution in which you have only first and second cumulant and nothing else. Okay? All right. Okay, so let's see now. Let's compute the. Sorry, here it should be sigma squared. Okay, so let's see now for the dice. So for the process of throwing a dice, the dice problem. So if I throw, yes? Is there a question? Is there a question? Yes, please.
Yes.
Tell me. What about?
What is also N standing for?
What is N standing for?
Yes.
So N is an event. So it's just an element of a set, okay, of a discrete set in general, right? So it could be, N could be the numbers between 1 and 6, N could be the probability of, could be the cars that are sitting in the parking lot out there, and I could compute the probability of throwing my iPad in the parking lot and picking and hitting one of the cars. And it could be something. I mean, it's just an event in general. Okay, is it clear?
Yeah.
Okay. I'm sorry for this. Nothing else came to my mind but throwing my iPad in the parking lot. So I apologize for this example that is a bit well, it's not very clever. Anyway, okay, so the dice problem. I said that we had the probability of getting one phase, which is 1/6, right? So suppose that now I want to compute what is N is just, in this case, is a number between 1 and 6. So my events are just the numbers between 1 and 6. Now I want to compute the average of N. Okay? So what is the average of N for the average? So if you throw the dice many times, what is the average number that you get out?
You throw the dice 10 times.
You throw the dice, what is the average number that you get out?
1 over the summation.
Well, how do we do this calculation? So it's the average number is by definition sum over n. If you don't know how to do it, use the definition. Okay, this is true for the whole course. So number n sum over n belonging to the set C of n Pn, right?
Yeah.
So this is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, right? Because the probability is always equal to 1/6, and n varies between 1 and 6. All right, so, and the sum is, I didn't write it down, so it's 24, 21, 21 by 6, which is 7 halves. No, not
3.5.
3.5. 7 halves. 3.5. Okay, 7 halves. Okay, so this is the average. Okay, so now let us use the same. Our AN in this case is just n. So now we want to compute. This is the average that you will get out when you throw your dice many times. What is the variance? Did you ever compute the variance of throwing a dice? I'm not sure. Did you? You did? Okay, what is it? What you get? Let's see. So, average of a, what do we have to do? Average of a squared, which is average of n squared. Okay, we have to compute this, which is by definition sum over n squared Pn. So I have to sum the squares and divide by 6. So it's 1 plus 4 plus 9 plus etc. plus 36 divided by 6. Now if I did okay. So then you have to subtract a squared. Okay? So a squared is 7/2, so the average of a of n is 7/2, and therefore the square of it is 49 divided by 4, right? And now what I have to do is, if I want to compute sigma squared, is I have to take n squared minus average of n squared. Now I don't have, I will certainly get confused if I redo the calculation here, but I invite you to check, okay, and then you'll tell me next time. The result should be, again, 7/2. Okay, which is again 3.5. So which means that essentially the fluctuations are as big as the average. Well, the fluctuations are not as big as the average because you should take the square root of this. Okay, so that compares to the average. So if you take the square root, sigma, which is the square root of n squared minus average of n squared, you get 1.8 roughly. Okay? So these are the fluctuations as compared to the average. That defines essentially the probability distribution. But this probability distribution, we know that it's a trivial probability distribution, it's just flat. Doesn't do anything. All right, so now, okay, I invite you to go through this calculation. Do it for the dice, do it for whatever you want, do it for the dodecahedron. It's just useful to get used to do calculations with probabilities. Now, it's useful because you will see it when we will do statistical mechanics that we will be thinking in these terms all the time about what is the probability to get a certain point in phase space, and then compute averages, compute cumulants of certain energy distribution, blah, 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 and so on and so forth. So it's important to have these concepts clear in mind. All right, now, yes.
35 over 12.
Sorry?
I got 35 over 12.
35 over 12.
Right.
Well, that's excellent. It could be that I'm wrong, right? Sometimes I am. I mean, I'm not saying I do calculations perfectly, also because I didn't redo this calculation recently. I just took it from some notes that I wrote last year. So it could be that it's wrong, so check it, okay? Check it slowly. I will do it myself, redo it myself, and let's see what comes out. Now I don't want to waste time checking this calculation at this moment. All right. Okay, so now in practice, there are two more things that we should introduce before getting to something a bit more advanced, which is the moment generating function and the associated cumulant generating function of a probability distribution. Now, it might seem to you now that what I'm telling you at the moment it's useless, right, from the point of view of statistical mechanics. But in a few weeks, you will see that we will be using the cumulant expansion, right, in order to compute partition functions all the time. And all of this is just straightforward probability theory. So if you understand it now in a simple setting, you will understand it much easier in the more complicated setting of statistical mechanics. So what is the moment generating function? The moment generating function is called g of t, is defined as the average of e to the a times t, where a is again my function defined on the set of events n. Right? So this is defined as sum over n belonging to C, e to the ant pn. All right. So why is it called the moment generating function? Because it's a simple exercise. Actually, it's not even an exercise. It's straightforward to see that if you take the nth derivative with respect to t of this function at t evaluated at t equals 0, you get a to the power n average. Okay? So that's why it's called the moment generating function, and in particular this formula implies that the series expansion of g of t close to t equals 0 has all moments as coefficients. I apologize, I'm using the same letter for the events and for the, okay, let's use a different letter. K, K, T, K, K factorial. Okay? So, it is essentially a function with series expansion as coefficients or the moments. Now, there is an associated function which is called the cumulant generating function, which is nothing but the logarithm of the moment generating function. Log of gt. Why? Because if I take the log, so I will have the log of 1 plus average of a times t plus average of a squared times t squared divided by 2 plus etc. 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 So now let's do a series expansion here, right? So I will have average of a times t plus average of a squared times t squared divided by 2 plus higher orders. So this comes, you know, from the series expansion log of 1 plus x, which is x minus x squared divided by 2, right? Plus higher orders. So now, if I interpret as x this, all of this, you see that this is just the first order, right? But now I have to take minus x squared divided by 2, so I will have minus x squared divided by 2, which is a average of a squared times t squared divided by 2 plus terms that go like t cubed, t to the fourth, etc., etc., etc. You see that if I stop therefore at second order, but I can go to higher orders, I will get that this is average of a times t plus average of a squared minus average of a squared divided by 2 times t squared plus etc. 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 Okay? Because of this combination of the expansion of the log and the series expansion of the function that I've done before.
Sorry.
Yes?
Can you go back to the previous?
Yes. You're so lucky. When I was a student, I had to take notes, and the professor would erase the blackboard immediately after, and that's it. Now you will have this lecture on YouTube, on the ICTP channel. You can listen to it as many times as you want. Okay? So don't worry about making mistakes in your notes. Okay, so you see that now this is the first cumulant, and what you get as coefficient of t squared is not the moment, but is the cumulant, right? So I can write this as k1, let's call the cumulant k with the letter k, so this is k1 plus k2 divided by 2t squared plus, and if I would go to higher orders, I would get k cubed, k3, the third cumulant of the kurtosis, divided by 3 factorial, and etc., etc. So in other words, the log of g of t, which is called cumulant generating function, is equal to sum over n from 1 to plus infinity of kn t to the n divided by n factorial. Oh, sorry, let's use again a k because n here is already taken. Or in other words, this tells you something interesting. Look at this formula because it's quite, I mean, I like these formulas. They're quite useful in physics actually. So this is the expansion in moments. And this is equal to exponential of sum over k from 1 to plus infinity of k, the kth cumulant, t to the k factorial. Okay?
K is the cumulant.
Yeah, I'm sorry. You want to use some other letter?
Maybe you can add tilde.
Let's use some other letter. M. M is a good letter. M. Okay? You see? So this is the... Alright. So this expansion that is sitting in the exponential is called the cumulant expansion of the generating function. Now, I'm telling you something as like... you know, they tell my kids, what I'm telling you now, you will understand when you will be old, right? So what I'm telling you now, you will understand in a few months. For us, the cumulant expansion will be a tool to compute the partition function as the exponential of something, cumulants, that sit up there. But it's completely analogous to this story. So when we will be doing the cumulant expansion for the partition function, remember that it comes from here. Okay? All right. Excellent. Yes?
From this moment generating function, you will get the partition function.
No, well, it's more complicated, as I told you. What I'm telling you here, you will understand in a few months. It's more complicated. We'll see.
Because I don't remember deriving this. They just give me the partition function.
Yeah, we will define the partition function. Don't worry. Don't get overexcited. I mean, all of this is like antipasti. You know what is antipasti? No. Okay. Well, because you cannot go to restaurants. That's problematic. So in Italy, before the main course, you have antipasti, right? Antipasti is before it means literally before lunch. Pasto is lunch. So and it's something that you eat just to as an opener, right? To get interested in eating, okay? So here is the same story. I'm telling you stuff to get interested in statistical mechanics, but it's not the main course, okay? All right, so another exercise that I'm not sure, again, I invite you to check it. So let's try again for the dice. Let's go back to the dice problem. So before we computed all these moments and cumulants by hand. But you see, it's very useful to have this cumulant generating function or moment generating function, because once you compute this function, you just take derivatives. You put it in Mathematica, and you don't have to compute sums of numbers all the time. Just take derivatives and ask Mathematica to compute. So it turns out that the moment generating function for this problem of dice, so A in that case was just n, the number on the face of the dice, right? And the moment generating function for this event, for this function here, is just the average of n times t, right? By definition. So this is equal to what? Is equal to the sum for n from 1 to 6 of e to the t to the power n divided by 6. So this is equal to what? Are you able to do the sum? What is it? It's a geometric progression, right?
Yes, it is.
You know, you call this thing R, and this is sum R to the n 1, 6, n from 1 to 6. And the result is you remember? Okay, if you don't remember, there is Wikipedia, Google.
Geometric progression.
Well, it's I don't, I mean,
ET power 7 minus 1.
sorry?
ET power 7 minus 1 over ET minus 1.
Correct. Absolutely correct. Okay, so she will tell you how to do the calculation, right? So it's a,
Oh, this one.
yeah,
It's in the high school.
yeah, it's high school, exactly. It's high school. So when you have a sum of this type, what is the result? It's r minus r to the power 6 plus 1, so 7, divided by 1 minus r. So overall, you get 1 over 6 e to the 7t minus e to the t divided by e to the t minus 1, right?
No, it's 1 minus r power 7.
Yes, but is this, so
1. It's correct.
right here I put a minus sign in front of everything. So I inverted the first numerator and denominator.
No, I mean the numerator. It should be 1 minus r power 7. Not r minus r power 7.
It should be 1 minus r power 7?
Yeah.
Okay, I trust you. I don't remember. Sometimes I'm, geometric. You're right. Okay, so then 1. All right. Yes, it's correct. Okay. Is it okay now, Professor? No, I mean, you're right. I made a mistake. I told you. You always have to check. I mean, the main concepts are always correct. But in these exercises, I invite you to redo them at home and check carefully. Okay? That's also part of the business. All right, so far, well, now if you take this probability here, you can calculate all the cumulants and all the moments, whatever you want. You take this function and you take derivatives and you compute the moments. You take the log of this function and take derivatives with Mathematica, for example, and you take and you get all the cumulants. Okay? Evaluated at t equals 0. So you see how useful it is. It's like doing the calculation in just one step, because then doing derivatives is much easier than computing sums of numbers, etc., etc. All right, so now one final thing we have to do today is the following. Okay, so far we have been talking about probability distributions that were defined on a discrete set. Okay, like number of faces of the dice, number of cars sitting there, and so on and so forth. Now, in physics, it's quite useful to define also probability densities that are defined on continuous variables. And I call them probability densities because it's like the difference of a number of cars and the density of cars when you just coarse grain, for example, the road here when there is a lot of traffic. So I don't think I have to, so you're all familiar with probability densities and things of this type. So let us just introduce two special probability densities that are very important in physics and in probability theory. The first one is the Dirac delta. The Dirac delta. So the Dirac delta is defined, well, is strictly speaking, is not a function, is a distribution which is zero everywhere and is infinite at one point, and it integrates to 1. Right? So you can see it as a probability distribution, probability density, not distribution. But, and if you now compute, for example, the moment generating function of this probability density, you will see that this is equal to e to the power t times a, right? So it's a very simple function. It's a very simple function because if you think for a second, this probability density has just one cumulant, the first cumulant, the average, and nothing else. Everything else is 0, right? So the cumulant generating function is trivial, is t times a, and nothing else. Now, is there now another special probability distribution for which the cumulant generating function is not just the first power in t, but perhaps also the second?
Gaussian.
The Gaussian distribution, right? So the Dirac delta has just the first power. The Gaussian distribution is also special.
What's L divided with?
Oh, I didn't. Sorry. You're right. N of t is just a short notation for the log of g of t. So it's the cumulant distribution function. All right. Okay. Now, the Gaussian distribution, as you all know, is defined as 1 over square root of 2 pi sigma e to the minus x minus mu squared divided by 2 sigma squared. And if you now compute the the moment generating function e to the tx, well, so you end up calculating the following integral. Divided by 2 pi sigma e to the tx. Now, this is one special instance of a class of integrals that are known as Gaussian integrals. This general formula, let me write it because we will use it. Where is it? Oh, I should write it, but I cannot find it. So the formula is integral between minus infinity and plus infinity dx e to the minus b x squared plus cx equal to square root of pi divided by b e to the c squared divided by 4b. Okay, so this is the Gaussian formula for Gaussian integrals. No, sorry. I think it's correct. And now, if you use this formula and apply it to the previous case, you will obtain that g of t is equal to e to the t mu plus sigma squared t squared divided by 2. Okay? So this tells you, therefore, that the cumulant generating function has a linear term, the average times t, plus a quadratic term, which is the standard deviation, t squared divided by 2. The variance and t squared divided by 2. Okay? All right. Now, why is the Gaussian distribution important? So important. Why is it so important?
It happened in so many natural distributions.
Why it happens in so many natural? So let me write. I mean, why is it so? Why is it occurring in so many problems in mathematics and physics?
Maybe because it's called normal distribution.
That's a consequence of the fact that it happens many times. That is called a normal distribution, right? But why it happens so many times? So in order to understand this question, right, I invite you to do the following exercise. Yeah, it's a simple exercise. It's not a difficult exercise. So we have been playing with a dice today many times. So do the following with Mathematica. Choose your program, you decide, right? Do the following simulation. Take 30 dice, right? And throw them. You can do it at home. I mean, if you have 30 dice, you can go buy 30 dice, and this evening, throw the dice, pick up the numbers, okay? So when you one throw will give you a set of outcomes, and I, where I runs from 1 to 30, and n is a number between 1 and 6. And now do the following. Construct the following variables, n, which is the sum for every outcome. You compute the sum from 1 to 30 of ni. Okay? And then throwing the dice many times, 100, thousands of times if you have a computer, plot the histogram of the outcome of this experiment. You know what is the histogram, right? You plot how many times you got 30, how many times you got 31, how many times you got 56, how many times you got blah, blah, blah. How many times you got, you see? So you will have, if you have 30 dice, right, you will have as possible outcome a number between 30 and 30 times 6, right?
Yeah.
So 30 and 180 are the two extremes, okay? And then, well, most probably there will be an average value that is in between. You check it. And then plot the histogram. How many times I got 30? How many times I got 31? How many times I got 66? How many times I got 81? And so on and so forth. And you will see that this distribution looks very much like a Gaussian. Now, sorry?
Because the peak is on the middle.
Because of something that is called the central limit theorem that we will discuss in a second, but it's a specific property of this type of process. Essentially, here what we are doing is summing identically distributed but independent variables. And it turns out that in physics, in mathematics, etc., when you sum many independently, identically distributed variables, the limiting distribution for many of such variables is a Gaussian. So that's why you see the Gaussian many times in physics and in mathematics, because of this property. But I invite you to do the experiment, and then if you don't get a nice Gaussian with 30 dice, do it with 60, and you will see that it's a better Gaussian. And if you do it with 120, it's even a better Gaussian. It gets better and better as you increase the number of elements in this sum. Okay? And next time I want you, next time is when? In 2 days. So you have time to do this exercise. It's very simple. Do it with a computer, because if you do it with 60, with 30 dice, you don't have time to do this exercise. It will take you a lot of time to throw 30 dice, register, etc., etc. But next time I would like you to not only to do this exercise and plot the histogram, but also to think about why this probability distribution looks like, it does not look like something like this or something else, but looks like a nice Gaussian with a nice standard deviation, etc., etc. What is sitting behind?
It's the probability of getting the mean is higher.
Oops, there's something that is, sorry, just a second, I have to share the screen again. Start broadcast. Yeah, the probability is higher, but I would like you to think about why the probability is higher, right? So do this exercise and think about why this probability distribution has a lot of probability of having events in the center and very small probability.
We have more ways to sum to that.
That's correct. Okay, you know it. Okay, but don't say it to everybody. That's correct. All right. Okay, so now this is the exercise for next time. Now let's see. I told you about the central limit theorem. So what is the central limit theorem? Central limit theorem is the theorem that tells you why the Gaussian distribution is important in physics and in mathematics. And it tells you the following. If X is the sum of many identically and independently distributed random variables, xi, where I runs from 1 to n and n is b, then the statement is, in the limit in which n is very large, the probability distribution of x, of the variable x, is a Gaussian. Okay?
When x is very large or n?
Now n is very large, not x. N is very large. Okay? All right, so how do you prove this? Well, the probability distribution of x is by definition integral dx1 dxn of p x1 pxn times a delta x minus sum over I xi, right? This is by definition. This is the probability of having a certain x. Now, let us compute the generating function, the moment generating function associated with this variable, which is e to the power t times x. Well, so this is equal to, okay, look, this is the beauty of technology, that things get paste. Let's paste it here. Wow.
By the way, Professor, is that capital N and small n?
Where?
In the dx capital N and then px small n.
Ah, yeah, you're right. This is a capital N. This is a capital N. Absolutely. Thank you. Okay, t times x. Right? And now, well, this is equal. If you now use the delta function and therefore substitute instead of this x sum over I xi, you see that this is nothing but integral dx p of x e to the t times x to the power n. Right? Why? Because if I substitute here this, I have e to the t sum over I xi, and this is equal to the product over I e to the t xi. And now you see that if I put here this product, the delta function is gone. I have just this. Okay? Okay, so now let us use the cumulative expansion. So this is equal to e to the k1 times t plus k2 t squared over 2 plus k3 t cubed over 6 plus etc. to the power n. Right? It's just the nth power of the moment generating function of a single event. That's the property. And therefore, this comes out to be equal to e to the n k1 t plus n k2 t squared over 2 plus n k3 t cubed over 6 plus etc. What?
I missed it.
You miss what? The previous? Here. Yeah, that's the problem of this artificial blackboard, but you know, the real physical blackboard is bigger. Okay? Can I turn the page? Okay. All right, so this is the cumulative generating function of the variable x. X is the sum over the xi's. Let us go from x to a density, right? So, in other words, let me define x tilde as x divided by n, or if you want sum over I all the way to n, xi divided by n. Now, it's easy, you can easily convince yourself that if you know the cumulant generating function of big X, the one of x tilde can be easily computed by just taking the one for big X and taking t divided by n. Okay? So that's very simple. You can easily just use the definition and we'll see that's correct. Okay? All right, so therefore, what is the cumulant generating function for x tilde? Well, it's, if you use this property, is e to the k1t, right? Because here I put t over n at this point, and you see that it eats up the n that is sitting in front. Then I will have k2 divided by n t squared over 2 plus k3 divided by n cubed t cubed over 6 plus etc. etc. Right? Now, you see that in this expansion, when you send n to infinity, well, practically all terms decay increasingly faster in powers of n. This justifies essentially keeping only the first and the second cumulant and holding, just canceling all higher ones. And in practice, it tells you that this is not only it's well approximated by a Gaussian distribution, but by a Gaussian distribution that has a first cumulant average of x tilde that is just given, but the second cumulant, k2, which is average of x tilde squared minus x tilde squared, k2 over n is equal to k2 over n. Sorry, let's call it k tilde, where k2 is the cumulant for the variable x. And in particular, it tells you that the variance, so this is a typical property of, in statistical mechanics, extensive variables. If you take the ratio of the standard deviation to the average, this scales like 1 over the square root of n. Okay? Where n is the number of terms in the sum. Now, all of this is, all of what I said right now is a general mathematical statement. If your x is the sum of independent variables and so on and so forth, then this and that. Now, you can easily understand where this type of reasoning will have some implications in statistical mechanics and thermodynamics. Because we have many examples in physics of variables that are sum of independently distributed random variables. For example, suppose that I give you a big magnet in a thermally agitated state, and I want to compute what is the magnetization. Now, the magnetization is what is known in statistical mechanics or thermodynamics as an extensive variable, right? Extensive means that essentially it's additive. If I add a piece of magnet, the magnetization will increase proportionally to the volume of this piece, right? So now you can think of picking your magnet, slicing it into many pieces. Into each piece, you compute the average magnetization, You compute your magnetization, and then since they are essentially uncorrelated, unless you're at a critical point, which is a special situation, but they're essentially uncorrelated, you can think of the magnetization in each single piece as a random variable, independently distributed. And therefore, the probability distribution of the total magnetization is going to be given by a Gaussian distribution with fluctuations that will scale like 1 over the square root of the number of particles, or if you want, the volume of the system. You see, all this reasoning based on the central limit theorem has a direct translation in statistical mechanics when we will be dealing with statistical mechanics. And on this reasoning are based many things, the equivalence of ensembles in statistical mechanics and so on and so forth. So it's very important. That's all I wanted to say. It's not just a mathematical curiosity. Okay? All right, so we are done for today, and on Friday we will first discuss this experiment for the dice, for the 30 dice, for those who have done it, and then we will be discussing the entropy. Okay? So, are you still there? Participants from abroad, from home. I don't see who is Yeshua, Pelus, Puya, and that's it. Okay, so we are done. I'll see you next time. Goodbye. No answer. Bye. Bye-bye.